393x squared plus, let's see, 2, what am I doing? Okay, 2 and 1, 3 and 1, okay? And x and minus 2.021. Perfect. I found the first derivative. Do I stop? No. I will continue with the second derivative because I need points of inflection if they exist. So then when I multiply here, what do I get? So this is 6, this is 8 and 1, 6 and 7, and I have 0, 0, and x plus 1.322. Good. S prime is never undefined. I have to set it equal to 0, and I do. So S double prime equals 0. I will get negative 0.0786x equals negative 1.322. So x will be in months. I will divide 1.322 1.322 divided by 0.0786. And I got 16.8, approximately 16.82 months. Now, what is the inflection point? This is not the inflection point. The inflection point is 16.82, comma, S of 16.82. So I have to plug this in and just get the number. But what is the significance? Well, we have to discuss this for the second derivative, just because that's the only question here. So of course I cannot have negative months, careful, although that's a polynomial function, is defined everywhere, but x is in months, so I cannot, not even this is possible, right? But I have to write 0 to infinity. And this is somewhere 16.82, and the second derivative is 0. Now I need to study the sign. This is the second derivative. Can you plug in 0 and tell me the sign?
Positive.
Very good. And when you plug in 100, I guarantee you, this will go to negative 7 plus 1, so it's negative. So obviously on this territory, the function is opening up, and here the function is opening down. So what does this mean? I'm not graphing the function. It means something like this, and then something like this, which means when the function is opening up here, everywhere, the rate of change, which is S prime of x, is increasing, is positive. I'm sorry, I didn't mean to write this, it's increasing. I said increasing, but I wrote as if I was talking about the function. So the rate of change is increasing. Now, here, the rate of change, or S prime, is decreasing. See? Big, positive, big, 0, negative. That's what the inflection point tells us. The rate of change of the function is decreasing, and here the rate of change of the function is increasing. Any questions? Okay, I just wanted, I know I'm running out of time.
That second derivative, is that we see the second derivative or the first?
Say that again. So when the second derivative is positive, the function holds water. When it holds water, it's the first derivative is increasing. Its rate of change, which is the first derivative, is increasing.
Not the second.
No.
Okay.
No. When the second derivative is positive, the function looks like this. What happens to the rate of change? It's increasing. When the second derivative is negative, the function looks like this. So this is the function s of x. Not exactly. We're not graphing the function. I'm just giving an explanation. So
Okay.
when the function is opening down, because the second derivative is negative, its other function, the derivative, the first derivative, the rate of change, is decreasing. So I know I ran out of time. I just wanted to show you what I wanted to look at and continue to looking at this. So page 305, I'll stop. I will not do anything else. So 305. So nothing new in 305 in the sense that all the same, first derivative, second derivative, but this time we are asked to graph functions like these. Many of them are quite impossible. It takes a long time, but we're going to look at simple examples, simple rational functions, and we are going to discover more, which means asymptotes, vertical and horizontal asymptotes. That's it. That's the extra in here. So then we're going to look at word problems.